Thank you all for joining today. The goal of today's presentation is to give beginners a strong foundation to shader development, as well as seasoned veterans a bit of a refresher. During this talk, I'll try to answer the following questions, such as, what is a shader? How do you make a shader, with emphasis on Unity's Shader Lab syntax? How do you profile and debug shaders? And last but not least, what shader considerations do you need to make for mixed reality? Before I jump in, I wanted to give a bit of an introduction. My name is Micka. I'm a principal software engineer on the developer experience design team here at Microsoft. I've been at Microsoft since 2016, where I've been working on the mixed reality toolkit for Unity as well as Unreal. But before that, I worked in game development for about 10 years, working on everything from independent games to AAA games. Shader information could and does fill many books. We're going to touch on the sections below to give everyone a gentle introduction to shader development. And we have tons of slides to go over, but please feel free to ask questions, and I'll try to answer them at the end of this presentation. The first question is, what is a shader? And this is actually a bit of a tough question. To answer this question, let's first outline what problem shaders aim to solve. Almost every graphics talk starts with a diagram of the graphics pipeline, and this one is no exception. Most graphics APIs and drivers follow this pattern for taking application data and transforming it into an image. This is the process your GPU goes through many times per frame. The first step of this pipeline is the input assembly step. This step assembles vertices into several different primitive types, builds adjacency information, or assigns unique IDs to vertices. You can think of this as preparing data for the next few steps. During the vertex stage, the primary job is to transform a mesh vertex, which you can think of as a point, from local space to clip space. This stage also specifies any attributes that need to be interpolated across a triangle. This vertex stage always operates on a single input vertex and produces a single output vertex. Next is rasterization. This step determines how to take a mathematical shape, such as a triangle, and fit it into a 2D grid of pixels. It will also clip vertices against the view frustum so that you don't end up processing any triangles which cannot be seen. The fragment stage is a pretty flexible portion of the graphics pipeline, but it normally takes an interpolated vertex value and provides a color value on a per pixel basis. Normally this is where lighting or other surface effects are performed. Blending is the final step of the pipeline, and it generates the pixel color you see on your screen using a combination of pipeline state, the contents of the frame buffer, depth buffer, or stencil buffers. As you can see, there are many steps to go from a mesh to a pixel, but how flexible is this pipeline? Before about 2001, this pipeline was not very programmable. This was called a fixed function graphics pipeline. Graphics APIs contained explicit lighting models that allowed programmers to send in specific material parameters or lighting information. Fixed function programming was the way for a long time. The original iPhone and iPhone 3G used OpenGL ES 1.0, which was a fixed function graphics API. Even up to the Nintendo Wii, we were working with pseudo kind of fixed function graphics APIs. After years of working like this, developers wanted more control over the graphics pipeline. They felt it was a bit too restrictive. The solution to this is shaders, or small programs that run on a GPU during explicit pipeline stages. Here's where we answer the question of what is a shader. You can see here that the vertex and fragment stages now have a shader program attached to them. This allows developers to program what occurs during these stages. Up until this point, I've been lying to you a little bit. In reality, the modern graphics pipeline is way more complex, and the pipeline differs a little bit on tiled renderers, which you often find on mobile devices. For instance, in DirectX 11, graphics pipelines not only have vertex and fragment shaders, they have whole tessellation domain shaders, geometry shaders, compute shaders, which can run asynchronously to this pipeline. And then new in DirectX 12, we have things such as mesh shaders. Let's talk about the two most common shaders you encounter in mixed reality, which are vertex and fragment shaders. Sometimes I'll call a fragment shader a pixel shader, which is just another term for the same thing. So now we're on to section 2, which is how do you actually implement a shader? Remember, shaders are just small programs that run on a GPU during explicit pipeline stages, which is mostly true except for compute shaders. Just like traditional programs you write for your CPU, you have many languages to pick from when writing shaders. Most have a C-style syntax and contain math libraries built right into the language for things such as linear algebra, which includes vectors, matrices, dot products, cross products, etc. And in general, the industry is heading towards an HLSL language, which is the one used by DirectX, but you also can find things such as GLSL, which is the OpenGL and Vulkan preferred language. Then there's things like MSL, which is for Metal, which is run on iOS and macOS. And then some vendors, such as PlayStation, have their own language, such as PSSL. Just like other programming languages, shader code needs to be compiled. And most graphics APIs do this in a few steps, with all but the last step occurring at runtime, with the caveat that OpenGL still does all steps at runtime. But you start with source code, which gets turned into assembly, which then gets turned into a hardware-independent binary. This is all at compile time. And then at runtime, that hardware-independent binary gets turned into a hardware-dependent binary. Next, it's a developer's job to instantiate and bind your shader programs. Unlike normal CPU programs, it's the responsibility of you, the developer, to do this. This is where things can start to get a little bit tricky since we're used to having operating systems like Windows or Mac OS control the activation and destruction of our processes and CPU executables. Fortunately, we have tools like Unity and Unreal which do this for us, allowing developers to focus on the actual shader code. Unreal's approach is to abstract writing shaders into a visual scripting language, which you can see an example of in the top right. You place nodes and connect them to each other. Unity's focus is Shader Lab, which is a thin wrapper around the CG/HLSL shading language. One thing to note is in Unreal, it is possible to write custom HLSL, which is something you often have to do. And then in Unity, Unity's moving 100% towards HLSL instead of CG for their scriptable render pipelines. And they also allow developers now to do visual scripting via shader graph. For the remainder of this presentation, let's focus on Unity's Shader Lab, since it represents a pretty steep learning curve and is likely what you'll encounter most often when creating mixed reality applications. When you right-click in Unity's asset browser and go to create a new shader, you have a few options. The most common options you'll select are Standard Surface Shader or Unlit Shader. Unity's Standard Surface Shader provides an easy-to-use interface for working with Unity's lighting pipeline, but that lighting pipeline is a bit too expensive for mixed reality platforms like HoloLens, so it's best to start with an unlit shader when creating one from scratch. When you create a new shader in Unity, it automatically fills out the shader file with a bunch of boilerplate code. Let's look at the anatomy of this code. Unity puts all shader types, vertex, fragment, geometry, etc., in a single file to help organize developers. Optionally, you can break shaders up into include files, which we'll talk a bit more in a few slides. The first line to look at is the shader's name. The name should be unique and is what will appear in the editor in the shader dropdown when working with materials in Unity. Next is the properties block. The properties block is a section of code where you list all the variables you want to display and serialize in the material inspector. These variables can be colors, textures, floats, vectors, and this is an opportunity where you can provide defaults. So for example, here we've defined a new property named _main texture or main text, and this is a 2D texture that defaults to a white texture. Next is the subshader block. Shader files can specify multiple shaders in a single file, and Unity will automatically select the first shader that runs on the current platform. So for instance, you could write a shader that runs on a HoloLens and another one that runs on an Android phone, and Unity will conditionally select the correct one. Honestly, we don't use this too often in practice. We normally just write one subshader, but it's good to know you have the option. Tags are used for specifying metadata that the engine can query. It gives the engine hints on the shader's usage. So examples are specifying the render type. Is a shader used on opaque or transparent objects? Another example of tags are tags to disable batching or force no shadow casting or ignore projectors. The level of detail or LOD property is used in conjunction with subshaders, and it allows you, the developer, to tell the engine how computationally demanding a shader is. This isn't automatically calculated. It's up to you to kind of profile and figure this out. But if you use this property at runtime, you can set the shader LOD value for a single shader object or for all shader objects in your engine, and then Unity will prioritize subshaders that have the lowest LOD value. In practice, this isn't something I see people use very often unless they're writing shaders that are meant to target a low power mobile phone and a high power ultra PC. Unity allows materials to be rendered in multiple passes. This is where the passes block comes into play. You can think of each pass as an extra draw call, and in mixed reality, we're always trying to limit the amount of draw calls we admit. So I tell people, try to limit your shaders to one pass. Passes specify not only the shader logic, but also the render state. So now we've made it to the CG program block. This is where the actual kind of shader logic or shader programming comes into play. You're no longer in Unity's shader lab syntax. We're now all in strict CG or HLSL code. That all lives between the CG program and NCG tags. The first thing we encounter are the entry point pragmas. This simply tells the compiler the respective entry points. So for instance, our vertex shader main function name is vert, and the fragment shader main function is called frag. Next, we're going to talk about shader variant pragmas. In this situation, we're defining a pragma called multi-compile fog. And while fog in MR isn't very important, shader variants themselves are very important for performance. So I'm going to go a bit on a tangent and take a closer look at them. Let's pretend we have a shader with many features that were requested by our art or design team, but not all features are needed 100% of the time. To avoid unnecessary calculations, we could branch on each feature, but branching isn't free. For instance, vertex shaders run for every vertex in our mesh, and pixel shaders are run for every pixel that's visible, and branching can get expensive. Which leads us to, how do we make this less expensive? And the answer is, the fastest code is the code which never runs. To ensure code we don't need never runs, we could maintain a shader permutation by hand that includes or excludes each feature. But you could see how that quickly could become a nightmare to maintain. The solution is to use Unity's shader compiler to automatically compile in or out features for us. So in this example, say we had a emission shader feature defined. If that feature is defined, we add an emissive color to our output. We can compound features together. So in the first example, if emission and channel map are defined, we add an emissive color multiplied by a scalar. Else we just add an emissive color, or else we do nothing. So in this particular scenario, we would generate 3 different shader permutations. And Unity provides 2 ways to define shader variants. One is multi-compile, and the other one is shader feature. These pragmas get defined at the top of your CG program block. The multi-compile pragma tells the shader compiler to generate a new shader for every keyword and package it with your build. On the other hand, Unity also provides a shader feature pragma, which tells the shader compiler to generate a new shader for every keyword and package it with a build if it's referenced by a material anywhere in one of the levels you're packaging. With this information, I recommend using shader feature whenever possible to avoid shader variant explosion, which means way more features packaged with your build than you actually need. I would only use the multi-compile shader Pragma when you need to enable or disable features at runtime and you're unsure which ones you actually need. Most Mixed Reality Toolkit Unity projects ship with thousands, sometimes tens of thousands of shaders, so that's kind of the level you can expect. Now that we've kind of completed our tangent, let's jump back to the anatomy of Unity's default Unlit shader. Include files. Just like in C and C++, you can put common functionality in header files. The Unity cg.cginc includes common Unity macros and functions. If you want to inspect the source code of any Unity include file, you can find them online on the Unity download archive. You just select which engine version you're using, and you can download the built-in shaders zip file. Moving along, the next thing you'll encounter is a structure, which is the vertex input. This structure normally is named appdata, but that's just a suggestion. You can name it whatever you want. And it contains data being sent into the vertex shader from the app's data, which is traditionally mesh data. Within this structure, you'll find vertex attributes. At minimum, you need a vertex position attribute tagged with something which is called a semantic. And in this case, you tag your position attribute with the position semantic. Other semantics, such as text chord 0, are more for the developer than the actual shader compiler, so you have a little more opportunity to name these whatever you want. Vertex output is the next structure you'll encounter. In this case, it's called V2F, which stands for vertex to fragment. Again, V2F is Unity's default name. It's not a requirement. And the job of this structure is to pass data from the vertex shader to the fragment shader. Each value within the structure is interpolated across a triangle before being passed into the fragment shader. And at minimum, you need one property which is tagged with the SV position semantic, and this tells the shader compiler that this is the vertex position. Variable declarations. So earlier in the properties block, we defined a underscore main text property. Now we need to actually define that variable. This is just like defining member variables in a C# or C++ class. In this instance, we've defined our underscore main text variable as a two-dimensional texture or a sampler 2D. Below that sampler 2D, we've also defined a similarly named variable called underscore main text underscore st. This is just Unity's syntax for defining UV offsets and scaling values into a 4-component vector. It's used later on by the transform text macro, which we'll talk about in a bit. The vertex shader. So we've finally made it to the vertex shader function. This is the entry point for all vertex processing. In here you can see the input is a appdata structure and the output is a V2F structure. In the vertex shader, the first thing we do is define our output structure. We then transform the local space position to clip space, which I'll talk about how that works in a bit. And then we specify the UV coordinate to interpolate for sampling our texture later on in the fragment shader. You can see here that the UV coordinate is wrapped in this transform text macro, and all that's doing is taking the UV coordinate, which is specified in the mesh, usually specified by an artist, and then allowing whoever authored the material to offset that UV position or scale it so it tiles or whatnot. So I've mentioned a few times taking a vertex from local space and converting it into clip space or screen space. Whenever I say that, I usually mean we're doing a few matrix multiplications. So in this case, the model view projection matrix. And that's what Unity wraps into the Unity object to clip position function. So first thing you do is take a local space mesh position, which is usually how an artist authors a mesh. You multiply that by the model matrix to get it located somewhere in your scene. You then multiply that by the view matrix, which is the camera's position and orientation. You're then going to multiply that by the projection matrix, which defines kind of the field of view of your camera and the aspect ratio. And at that point, you finally landed in clip space, which is what the rest of the graphics pipeline uses for processing. We've now made it all the way to the fragment shader. This is the entry point for actually shading pixels. So you can see here the input is v2f, which was generated by our vertex function, and the output is a single pixel color, a fixed 4, which is just a way of specifying 4 floating point values. You can technically have multiple outputs from a fragment shader, but we're going to work with just one because that's the most common case. So the first thing we're doing in this fragment shader is sampling a texture. We're taking the underscore main text sampler 2D property we specified above, and we're indexing into that texture based on the current UV position. From that, we get a color. We then fade that color based on fogging values using this Unity apply fog macro. You can kind of ignore this because normally we don't worry about fog in mixed reality, since fog is used to kind of fake atmospheric light scattering of faraway objects, and most objects in mixed reality are relatively close to our view. We don't normally have to worry about rendering mountains that are kilometers away. And then the last thing we do is return the color. So we sample the texture, applied fogging to it, and then return the fogged color value from that texture. So that's it. We now have a beautiful unlit shader after going through all those steps. If you wanted to take your unlit shader and make it a lit shader, that's as easy, quote unquote, as adding lighting equations to the pixel shader. One of my favorites is using the n.l kind of algorithm, where you take the normal of the surface, dot product with the direction that the light's facing, and then you can kind of get a nice shaded color. You can also experiment with more advanced algorithms such as physically based lighting. From here, let's talk about materials and render modes, which go hand in hand with shaders. The term material and shader often get interchanged or confused with each other, and they're not quite the same, which we'll explain. Materials are more properly defined as something that encapsulates a shader or a container around a shader. You can use one shader for multiple different materials, and materials specify the inputs that are passed into the shader, as well as any render state that the graphics API should be notified of. Render state is kind of an overloaded term, but it pretty much tells the graphics API how to blend a material with other materials that have already been rendered, how to cull a material, should the back faces or front faces of the polygons be removed. It also tells the graphics API if this material should write to a depth buffer, if it should read from a depth buffer, how it should sort the object when being rendered, those types of things. In this diagram, we're showing off 5 different render states. On the top is the name for what Unity calls these discrete render states, and on the bottom is what Unreal names these 5 different discrete render states. Technically, there are thousands of different render state permutations, but these are ones that come up pretty often in mixed reality. So opaque objects are objects which block all light. You can't see through them. Cutout or masked objects are binary opaque or transparent objects, so they're either or. Fade objects are non-physically based lighting, so as you start to make the object more transparent, lighting is not preserved like the real world. And there really isn't an equivalent to this in Unreal that I've found. Transparent or translucent objects define objects which allow light to pass through them. So you could think of a window or a water glass. And then additive objects add light over top of existing ones. So whenever you use these, they'll make the object appear to glow over top of any objects that have already been rendered. Next, let's talk about some considerations you need to make for your shaders and materials in mixed reality. HoloLens 2 is a mobile stereo headset, which means when you're authoring shaders or materials, you need to make a few concessions for performance. The first thing to think about when writing a shader for mixed reality is how can you reduce the amount of fill rate pressure that your shader has. And fill rate you can summarize as the number of steps it takes to render a pixel. Those steps can include how many objects it takes to render or process a particular scene, the number of operations in your shader, the number of GPU stages for your final pixel result. So if you're doing any geometry shaders or post-processing effects, that puts more pressure on fill rate. And then the number of pixels you actually have to render, so how high resolution your final image is. And fill rate has a huge impact on most mobile graphics cards, especially stereo ones like you find on HoloLens 2. So to reduce fill rate pressure, you're going to want to opt for the simplest shader possible in mixed reality, which usually means using Unlit or mobile shaders you find in Unity and Unreal. If you do need lighting for your materials, then fortunately in the mixed reality toolkit for Unity and the mixed reality toolkit for Unreal, we have some custom shaders which are optimized for mixed reality. They include the mixed reality toolkit standard shader in Unity, and within Unreal, in our graphics tools plugin, we have a GT default lit material function. When rendering an image in mixed reality, remember it's stereo, so that means you're rendering an image for the left eye and right eye. And the unlit shader we walked through earlier in this presentation, if it were to be dropped into a mixed reality project, it'd likely be broken. And what I mean by broken, objects would only render in your left eye and nothing would show up in your right eye. To improve stereo rendering performance in mixed reality, Unity and Unreal use something called single pass instance rendering. You'll sometimes hear that called SPUR to improve performance. SPUR reduces draw call counts, which is a great CPU win, and improves GPU cache coherency, which is a nice GPU win. Here you can see rendering of the left eye and the right eye. Multipass rendering to both eyes synchronously, and then single pass is rendering to both eyes at the same time. To support single pass instance rendering, you need to make a few small changes to your shaders. It comes down to changes in 3 places. First, you need to add an instance ID macro to your appdata struct. Next, you need to add a stereo output macro to your v2f struct. So far we've added 2 macros to the bottom of our 2 structs. And then last but not least, you need to initialize your vertex output structure with 3 macros right at the beginning of your vertex shader. Note the fragment shader doesn't need to be changed at all, and that's it. The Unity documentation also has a few more details for how to handle this with post-processing shaders and geometry shaders. Now let's talk about performance and optimization tools for shaders. Unfortunately, shaders are a bit harder to profile than code running on a CPU, but we have some tools. I always recommend developers start with a coarse profile of their application using the visual profiler found in MRTK Unity and Unreal. If you're not using MRTK, that's totally fine. In the Windows device portal, there's a frame rate counter under the System Performance tab. And if you still want to use the visual profiler but not MRTK Unity, the visual profiler is a single drop-in file you can find on GitHub. If you find your app is running slow, then the next thing to do would be perform a deep profile. Unity has a great profiler for this, and so does Unreal, called Unreal Insights. If you take a deep profile in Unity and see that graphics.waitForCommands is taking the most amount of time in your frame, you're likely CPU bound. And if you see graphics waitForPresent taking the most amount of time, you're likely GPU bound. If you find you're GPU bound, try enabling the GPU usage profiler within the Unity profiler. It's normally disabled by default. This will help tell you what part of the frame is slow, whether it's rendering opaque geometry, transparent geometry, or maybe some certain effects that are occurring. If you still need more information, you can also open up the Frame Debugger. The Frame Debugger is a tool that allows you to step draw call by draw call through your scene to see how it's actually rendered. A great feature of this tool is it will also show you the inputs to your shaders, so you can actually see what values are being passed in. Another great feature of this is it can connect to HoloLens remotely. So you might be asking, this is all great, but how do I actually profile a shader? There are 2 popular routes for profiling in MR. The first is pix. which allows you to see how long an object actually takes to render on a platform such as HoloLens. And Pix is a GPU and CPU profiler for DirectX apps that gives you very accurate timing results. With this, you can infer how long it takes your shaders to execute on a particular draw call. One caveat is Pix is suited towards DirectX 12 development. Unity 2020 still uses DirectX 11 for HoloLens 2, and Unreal Engine 4.26 does use DirectX 12 with OpenXR, but it still uses DirectX 11 when you're using the Windows MR plugin for HoloLens. So with that information, another recommendation is to use RenderDoc. And this is a great segue into our next topic, which is debugging. Let's now talk about how you can debug a shader. Unfortunately, shaders are also a bit harder to debug than code running on a CPU, but we have some tools. When you want to debug something quickly, we often turn to what's called printf debugging, and you can do something similar in shaders, and you do that by returning specific colors when a statement is true. So in this example, whenever the UV coordinate along the x direction is less than 0.5, we return a constant red color. That way, any red pixels will pass this condition, and any ones that aren't pure red fail this condition. You can think of this kind of like as a debug log here in Unity. Remember, if you just want to purely sanity check the inputs into your shader are correct, you can always use the frame debugger. If you actually want to debug the flow and state of your shaders, this is where RenderDoc becomes especially important. RenderDoc is a popular open source graphics debugger. It has great integration with Unity and Unreal and documentation to help get you started. RenderDoc allows you to step through your frame just like Unity's frame debugger, and it lets you step through shader code kind of as you would in Visual Studio. It's great for sanity checking the disassembly of your shaders and the current values of any of your variables. Note, you aren't debugging a live application. You're taking a snapshot of your application and doing post-mortem debugging. By default, when debugging in RenderDoc, only the disassembly is displayed. You need to tell Unity and Unreal to generate symbols for your shaders. To do this in Unity, it's as simple as adding a Pragma to the shader you wish to debug. And Unreal, it's a project-wide setting, so you need to enable 2 config variables. So we're nearing the end of what I wanted to talk about, but before I kind of send you on your way, I wanted to give you some additional resources to check out. One could spend their whole career learning about shaders, and here are some resources that have helped me along the way. Unity has a tutorial right within their documentation that shows you how to write vertex and fragment shaders. These tutorials slowly snowball or build upon each other to introduce more features as you progress through the tutorial. There's also a blog called Cat-Like Coding, which has tons of useful information about how Unity's rendering pipeline is set up. The great thing about these tutorials is they expose bits and pieces that Unity doesn't within their documentation. Even though OpenGL is getting a bit old and some would say it's on its way out, it's a great way to learn the whole graphics stack. I learned OpenGL back in school, and you may be tempted to learn new APIs like Vulkan or DirectX 12, but they have a very, very steep learning curve, so this is a bit easier of a way to get your head around how Graphics API might function. Last but not least, I wanted to talk about ShaderToy.com. ShaderToy is a website that allows you to iterate on shaders right in your browser, compile them, and view them. Another cool thing is it has a library of shaders people have written, so you can learn a little bit from some of the best shader artists in the world. And ShaderToy has also been pioneering ray marching and sign distance fields to create beautiful images just with shader code. It's worth checking out. Thank you so much for joining today. Shader programming is a complex topic that I find I'm learning something new about every day. So if you have any questions, please don't hesitate to reach out and ask. Thank you.